Okay, we're going to start our introduction into confidence intervals right now. And to start with, I'm going to do a bit of a review process here. So, if you recall, we were talking about normal distributions and we had different types of population distributions. Perhaps we had perhaps we had a bell-shaped population, maybe representing all the different shoe sizes for people in the world, and it took on a normal shape, with maybe size 9 there in the middle being most popular. So it has most occurrences in the middle. We would always have, these would be symmetric. This is a symmetric matrix, meaning it has the same area to the left as it does to the right, even though it doesn't look like I drew it that way, but that's the case. So it'll have a mean and some general standard deviation, and some point that we're interested in, we always called x, value x, that was the variable. And we might concern ourselves with the area to the left, or possibly the area to the right of this x value. And there's other combinations we can have. We could have more than one value, and we can find the area in between the two. But the key thing here, the key idea here, is that we're talking about population distributions. So this was like a normal distribution, and we spent a lot of time talking about normal distributions. But we could have other types of distributions. They could be any shape. But one of the shapes of distributions that we had when we were talking, well, about let me use a different. Let's get rid of that. So one of the things we were talking about, all my keys and stuff are not necessarily in easy reach for me, the way I'm set up here. Um, let's use this. So I have to go from the top down. I'm 2 weeks and I forgot how to do this stuff. So we might have a distribution that that is, the maximum values are all the same. So we might have, this might be a discrete distribution, and we did this for the die rolls, where we were talking about the ideal situation. I tack on another block here. This guy was uniform, but it did make up a population distribution. In this case, we also had a mean and a standard deviation. And for this one, the mean for this particular distribution, the mean was 3.5, and the standard deviation was 1.708. But instead of a normal distribution, this is uniform over here. But these were population distributions. So we could draw, and we did this in class with dice. You rolled 2 dice, and we drew a sample essentially from this population. And when you rolled 2 dice, one of these numbers randomly came up, and you added them together, and you found the mean of that distribution. So when we do that, and we could do the same thing here. We could grab a certain number of samples, and we could create what we would call, and in both these cases, so this is population. In both these cases, we created a different type of distribution that we called the sample mean distribution. And if our sample size was large enough, or if our original distribution was a normal distribution, then our sample mean distribution always turned out to be also a normal distribution. And the mean here the mean of our sample mean distribution was equal, always turned out to be equal to the mean up here. And we did the same thing over here. Um, we compared all our values and we found out that we could create a discrete, idealized discrete distribution here that actually would represent, boy, that's a really small plot I'm making here, but this would ideally represent the situation, the ideal situation. And here in the center, the average of 2 die rolls, remember when n was equal to 2, or two die sample set, let's call it, if we're going to use statistics words, a 2 die sample set. So we had two numbers, we found the average. So we found the average, and we have the means of these things. So if you recall, we actually plotted 1,000 of those picks. We did this 1,000 times. I did it with a computer program. You can look back in the notes when we're talking central limit theorem, and I think I can do that actually. I'll look back here. So reviewing some of this stuff, if you want to look this over, you will see that what we did was, so here was how when we created the pyramid distribution, or the idealized distribution, which was a representation of the full sample space. This is the idealized, and then I had you guys roll 2 dice, and you took the average, and then we figured out all those averages, and I don't have any of that information written here, but we figured out all those averages, and I created a very large, you know what? I just went and checked the other classes notebook page to see if we had those plots, and I don't have them. But we did create them, and if you recall, we did this experiment with thousands of cases, and it looked close to a mound-shaped population distribution. So really, this is the central limit theorem at work. And recall, central limit theorem, recall that when we do this, we found that, again, the mean of the sample mean distributions, either one of these, was equal to the mean of the population distribution, and the standard deviation of this thing was equal to sigma over square root of n. And if you look back, you'll see that I showed how that came about. Well, the whole point of doing this was so we can get something we can work with and compare to a third type of distribution here, the standard normal distribution. So recall, with the standard normal distribution, we would have, let's try to be as neat as possible here. I have a bell-shaped distribution, or a mound-shaped distribution, but our mean in the standard normal distribution is equal to 0, and our standard deviation is equal to 1. And of course, up here, the standard deviation could be anything, and we can actually calculate a standard deviation here. I forget what it was, but the standard deviation could essentially be anything based on how spread out this sample mean distribution is. But we always know that the standard deviation of the sample mean distribution is less than sigma. So it has less spread. That's why I kind of drew it more skinny. It has less spread than the population distribution from which we pulled the samples. So we get the standard deviation or the standard normal curve, and we're interested then in figuring out what z is because we can go to our z tables and figure out what the area is under this curve. So typically for a variable, for a variable in the population, if we look up here, that's this top curve. For a variable up here, if we wanted to figure out some information associated with that variable and relate it to our z curve, our standard normal curve and z, we use this relationship, x minus mu over sigma. But now we have to go for our sample mean distribution. When we calculate z, we have to do it in a different way. We have to look at x bars now because x bars are like the variable here in this distribution. They're not x's anymore, they're x bars. They're means. So this is a distribution with a bunch of means created by a bunch of means of different values. And if you recall, when we did the simple situation in class, we rolled 2 dice, we took the mean of those 2 dice, and then your mean ended up somewhere to the left or right of 3.5. So we would take this x bar then, and then subtract off mu, and we'd have to divide it by sigma of the sample mean distribution, which we recognized was this other value. So I can substitute that in. So now you really want to work with a relationship that looks like this when you're calculating z for sample means. Sigma divided by square root of n. So that's a little bit of a review. And I think I'm going to stop the video here and start a new video. So I'll pick this up in another video.